We're going to talk a little bit about, wafers and what is a wafer. The predominant material system is silicon, and this is what is called a silicon bowl, and it's got a 4-inch or 100 millimeter diameter. And the way it's made is you get a molten solution of silicon, you put in a seed crystal, and you pull and twist it out. Now this is at a really high temperature, and so the surface oxidizes, right? But you're not really trying to make oxide here. It just is a byproduct. And the colors you see are the oxide is different thicknesses, and you get, it transmits at a quarter wavelength, and so, it's absorbing at one, reflecting back in your eye at another. And it's just, now we use that same kind of, what color is it tells us the thickness when we actually grow something on top of the wafer. We just slice these, right? So, a little bit, why don't you guys come around this way so you can see, is that over the years, the diameter of the wafers used in commercial fabrication has gotten bigger. So yeah, this wafer here used to be state of the art, right? And then we moved on to 3-inch, and this is 4-inch. And the pattern you're seeing right there is something that we make here in the lab, but it's transistors, but they're not interconnected. They're all like individual devices, which is something that, this might have been useful for. But when you want to talk about the economics, if you look at this wafer here, right, it's 300 millimeters, and you can see the same pattern again and again. And so if I tried to do that one pattern on this wafer just by overlapping it, I can fit about one of these, right? Now this wafer was donated by somebody from MPEL. It's not an Intel wafer, okay? And so, so each wafer would only give one CPU. Now when this wafer was in commercial production, we didn't make, several centimeter on a size dies. But then you move into this, and even here, right, I could probably get 5. And what you would have to do is use like 150 of these to get anything made, which if you look over there is a thermal furnace from the 70s, and that's exactly what they did. When you put it in that furnace, you can process 150 of these at a time. Now we process one wafer at a time so that we can better control the process. So, actually, if I were saying I want to control the thickness of this bowl, I have done a lousy job of it because you can see the color changes, right? Well, imagine I'm trying to get the thickness of something evenly distributed, the same thickness across the wafer. Now looking at this, yeah, it's about 400 angstroms, okay? But it's varying by more than what you would want. You just would need a tool to measure it. So, rather than do 150 wafers and worry about the variation from the front of the furnace to the rear, you do it one at a time and try to minimize the variation across the wafer for one shot at a time. And what you're going to be doing over there is actually taking wafers and scribing them into coupons to do advanced processes. Because what you do is you get a process working on a small area, all right, does it work, all right? And then you try to get whatever process you're doing uniform across larger and larger areas. Except they don't buy these wafers, they just take a 300 millimeter wafer and break it up into something called coupons. And that's what people at Applied Materials do when they're working on advanced processes is they take these wafers. And these 2 wafers on the bottom came from Applied Materials for a research project. So when you're over there scribing wafers and cleaving them and writing your name on it, that is an industry level activity. They do that in lab. Now the scribing, it's done with a laser, right? But you've got to keep track of what you do and when it's done. So yeah, this is a FOUPS. And yeah, in a modern fab, this wafer never, it's not carried around, but it's run around rails with robots from machine to machine. And when they measure something, it all goes into a database so that you can analyze it. Because it's just not enough to do it. You got to be able to track it. All right. So another thing here, this is a package for a CPU. What was it, Kevin?
Intel i3, 7th generation.
Yeah, he took it out of his computer. Okay. And what these are is, what is a chip? Because a lot of times, this part, the thing with the legs, is called the chip. But the chip is really, the thing with the legs is called the wafer carrier, and the thing inside is the chip. Now, this is a very small design as opposed to something like a CPU, but it was designed by San Jose State students, fabricated elsewhere, tested, and it was here. And this one is LT13 something. It's an operational amplifier from Linear Technology. All right. So we've got some other things here. How do you get these patterns? All right. Well, this is a quartz mask, and you can see a pattern on there. And wherever the light gets through is where this material called the photoresist will wash away. And when it washes away, you can etch it or do things to it. Now, this is a 1-to-1 mask, where if I place this on top of the wafer, I'm going to get a 1-to-1 transfer. In a modern system here, you would put this mask in something called a stepper, but it focuses it down, kind of takes the picture, steps, takes the picture, and just steps along. So they, rather than one at a time, the masks are done across the wafer. But that's a whole other class with photolithography, but that's where it comes from. Other things that you can do at this station, right, is we have some transistors that you can look on under a microscope. Most of what you're going to see are the boxes, the aluminum boxes where you would bond your aluminum wires to it. The transistors are actually, even for what we're doing there, are kind of small. And just, what else is here is we have an evaporator where we can deposit aluminum, and we have some various other processing equipment. But today is really just about getting used to the